everyone. My name is Brian Leota, and I'm Brentag's Product and Marketing Manager for the water treatment business in North America. Brentag is pleased to present this webinar today on water treatment challenges in the field. Hopefully everyone who wanted to participate is here and ready to go. This is one of many webinars that Brentag plans to present. We want to bring knowledge to our customers and help them improve the quality of service that they in turn bring to theirs. So in an effort to continuously improve our customer-facing programs, we encourage feedback from the participants about how we did today, the relevance and depth of the information, as well as suggestions for future programming. Our technical webinar series has featured topics such as heavy metals removal, anti-scalant technology, oily waste treatment, foam control, jar testing, bioaugmentation, DAF, just to name a few. For this presentation, we're going to highlight 4 different challenges commonly encountered in the field, each presented by a different speaker. The first topic will be BOD reduction. As population, and this will be presented by Dick McCarthy of Brentag Great Lakes, as population increases, the demand for food follows, and consequently the industry is facing stricter BOD discharge limits. So Mr. McCarthy is going to discuss the challenges he's experiencing with BOD reduction and present recommendations to solve these complex challenges. Next up, we'll have Tom Dobson, Brentag Northeast's Water Additives Manager, who's going to discuss molybdate and other metals restrictions and limits. Tom is going to talk about the restrictions in New England and seeing tighter limits in metals such as nickel, lead, and zinc. And Tom is going to present some novel treatment ideas. Next up, we're going to hear from Katie Kelleher, our industry manager in Brentag Canada, who's going to discuss treatment approaches and determining the best approach. Specifically, she's going to talk about the differences between soluble and insoluble contaminants and the implications and how this relates to designing a treatment program. And finally, Kevin Cope, our Brentag North America Applications Specialist, will discuss water reuse and conservation. He's going to present several water reuse and water conservation challenges he's experienced in various industries, and he'll also discuss possible ideas for solutions. So at the end, we're going to attempt to save some time for some Q&A. In the event that you have a question that we don't get to because of time, we'll provide contact information so that you can email your questions and they will be answered. Also, a PDF of today's presentation will be made available to any participant on request. So without further ado, we're going to start with Dick McCarthy. Dick, take it away.
Good afternoon, everyone. Like you said, my name is Dick McCarthy. We wanted to talk about BOD reduction in the food industry, and a common theme that we've been seeing. So if you break the food industry down into 3 main segments, you have your more full-scale meat and vegetable processing, rendering, full meat scale. And then on the middle, you have kind of the liquid ingredient, small-scale processing, and that's mainly who we're going to be focusing on today. And then you have the food packaging, where they're taking food and just kind of putting it in the final packaging, flash freezing. Those customers really don't produce much wastewater. So we're really going to be focusing on the liquid ingredient, small scale processing, where they have some wastewater production, but they definitely don't have their own wastewater treatment process on site. So historically, this middle group creates small wastewater streams, and these streams might have some pH adjustment. They might be monitoring BOD or TSS, but there's really no wastewater treatment, so to speak of. They're creating the wastewater, maybe adjusting the pH, but other than that, they're discharging directly to the municipality. So as the communities grow up around these municipalities, they begin to stress out the municipalities, flows can become maxed out, treatment can become maxed out, and really it puts a lot of pressure on these municipal wastewater treatment plants. And their choices are to either spend, millions of dollars pouring concrete and expanding, or they can cut down on what's coming to them. And that would either mean putting more taxes or limitations on the citizens, which isn't really feasible, or they turn to the industries themselves and have them tighten up their discharge limitations or they can impose some pretty hefty fines or surcharges on their BOD limits. So these food companies become tasked to lower their BOD, which poses several problems. Often they don't have a full-scale wastewater treatment plant. They can't just increase chemical feed or the amount of mechanical treatment because there is none. They have no guidance, because they don't have a wastewater treatment plant, they don't have wastewater operators or experts. So they really don't have any inclination of what to do to reduce BOD. And pouring concrete could cost them $500,000 easily if they reach out to an engineering company and they need to put in a full-scale wastewater treatment facility, not to count electrical operators and chemicals on the daily or annual basis. So this is where the opportunity comes in. The opportunity for a water treatment industry to reach out and help solve a problem. We have the opportunity to walk them through the process since we have the expertise of what's going on and what their options are. We can reach out and be a resource for the customer and let them know what can be done and what the general costs are going to be. So what can be done? Well, some of the options include chemical treatment. If they are already treating pH and monitoring TSS or BOD, then the odds are there probably is some place to add a coagulant and maybe a small filter press and take out some of the insoluble BOD. There's also an SBR, which is a sequencing batch reactor with a biological component. Often these can have a rather small footprint. It's just a passive system with a biological component. Basically, the wastewater flows through, and the SBR can really go after a lot of that soluble BOD, especially if it's a plant that deals a lot with sugars. You would still need some mechanical treatment, most likely to take out some of the solids after this. The wastewater, especially if it's a very low flow plant, they could have the water hauled off, land applied, or used for feed. And a full wastewater treatment plant, such as a DAF or a belt filter press, it is an option, especially if they're getting up around $500,000 in fines. So guidance is the key. You really want to focus on becoming a resource for the customer, somebody that they can trust, somebody that knows the systems, and somebody that can kind of help guide them down one path or another because you know the resources your customer has at hand. We want to know the regulations. We really want to dig into not just what they want to achieve, but also what the regulations being pushed on them are. We want to make sure that the customer knows that there aren't really bonuses for going much further than those regulations. So we really want to guide them on achieving what is needed based on the regulations passed down from the municipality. Goals. We want to know what the goals of the customer are. Yes, there are those regulations, but the customer might have other goals in mind, such as only needing one operator to run whatever system we decide on. Safety might be their primary goal. They also might want to ever not have a hazardous chemical on site. It's really key that you understand what your customer's goals are beyond just achieving lower surcharge limits. And decision makers. We want to make sure that the person we are having these discussions with is a decision maker, or that we can bring the decision maker inside. And this kind of rolls back into knowing the goals and the regulations and being that resource. You don't want to be working with just one person who ends up not being the decision maker, and then you find out several months down the road that the real decision maker has been working with somebody else the whole time. So it takes tact and diplomacy to end up working with a decision maker, especially if that's not who you're with in the beginning. But finding out and recognizing who that decision maker is going to save you a lot of headaches in the long run. And timeline. It's very important to know what the city's timeline is on their surcharges, but also what your customers' timelines are. If they have a very long, stretched out timeline, then you want to make sure you've got pivot points in between and you're hitting deadlines, and you're making sure that you don't just pitch them an idea and then leave it in their court for 6 months. So how to identify a need? Well, as we all know, our customers' patterns can change. So we want to be continually asking them some of these questions. Is BOD a concern? As we all know, the BOD loadings can change over time, and the city's limits can change over time. Is oil a concern? A lot of customers build up oils, and these oils can definitely have a large effect on chemistries in the process. Are grass products required? Some of your customers might not know that if they're producing a sludge that's grass certified, it can be hauled off for live feed. Can they treat the materials that are being hauled off? If your customer is facing new limits, maybe they can treat the materials that are being hauled off instead of hauling them off. As freight becomes more expensive, as freight drivers become rarer, hauling off might not be the best option anymore. Are there surcharges from the city? Often a customer just gets used to surcharges and they don't identify it as a problem to you. And your customer will generally have a flat rate or fee based on the amount of water they're discharging, and then kind of a mid-level BOD or TSS rate. And then anything above that, they'll generally call a surcharge or a fine. If they get used to these surcharges, they may not realize that there are other options out there. It's important to ask those questions. Is reuse an option? Can that water go back into the plant in some way or another? If there's a lot of cleaners or chemicals in it, maybe it can still be used. And are there incentives for going green? Sometimes a customer can get credit back to them for going green, and this can be things like replacing a inorganic hazardous product with an organic non-haz product. It's really based on the initiatives that your customers are looking at and maybe the initiatives on the city. In conclusion, we really need to push ourselves, both as operators or sales reps or managers, to ask questions of our customer. We want to know the ins and outs of their business. We want to talk to as many people at that business as possible, and we want to keep asking questions. Questions based around the fluid flows, quality, and regulations. As we all know, customers' flows can change over time. The quality of those flows can change as well. They can have more oil, more BOD, more TSS. All of these things can change. It's a very fluid situation. And the regulations can change over time as well. It's important that we are continually asking questions of our customers, and really pushing our reps to ask these questions as well. Continually asking them, what are the regulations you expect to see next year? Do you expect your flows to change or the quality of your water to change? Our customers are in an ever-changing battle to get the best water quality at the best economical price. And it's our responsibility to help them get there.
Thank you, Richard. Next up, we've got Tom Dobson, who's going to talk about molybdates and other metals restrictions. Tom?
Thank you, Brian. Good afternoon, everybody. As Brian said, I'm Tom Dobson from Brentag Northeast. And today I'd like to talk to you about molybdate and other metals restrictions in water treatment. A few years ago, we started hearing that molybdenum was starting to come under scrutiny by the EPA, and they were thinking about adding it to the heavy metals list that they would like to see regulations placed on. We've recently found out here in the Northeast that one such state, Massachusetts to be exact, has done that, and they have lowered the limit of the molybdenum to the point where using it as a tracer in a cooling water or boiler water treatment program is no longer possible. And since it's not being able to be used at a 2 to 5 part per million treatment range for a tracer, the use of it as a corrosion inhibitor then definitely is not possible, because we generally feed higher feed rates when using it as a corrosion inhibitor. So the regulatory restrictions that came about were that they didn't go to each wastewater treatment plant, municipal wastewater treatment plant, and ask them to tighten it. They just said to everybody in the state of Massachusetts, because they figured there were so many widespread users, particularly a lot of cooling towers and boilers, that they please asking them to eliminate the use of molybdenum from their products. I'm then going to talk to you about the replacement chemistry that we can use for molybdenum, both in tracing and corrosion inhibitor. I'll present a lead case study from a lead acid battery manufacturer and a nickel case study. In both cases, these industries were hit with lower limits and had to make corrective actions from the conventional chemistry they were using. So as I said, the municipality is adding molybdenum to discharge permits, and levels are so low that even tracer must be eliminated, and we can't use it as a corrosion inhibitor as well. So we're looking for alternatives, and widespread use of molybdenum is no longer possible. So the alternatives that we have at our fingertips, on the tracing side, it's more common now that PTSA tracing dye is being used. It's a very unique vehicle to trace your product because you can measure it with a handheld fluorometer. There are also pieces of equipment that will monitor and control the feed. Of course, this gives you very fast results, but I would suggest that you also check the other chemical balances in your system and not just rely on a fluorometer test result and say we're good. Corrosion inhibitor replacements that are possible for us are sodium nitrite, which I'm sure all of us know. Tannins are now making their way into water treatment, everyday water treatment products. HPAA, or hydroxyphosphanoacetic acid, is an excellent mild steel corrosion inhibitor when used in conjunction with zinc, and I've seen it work very well in saltwater systems. The metal precipitant chemistries that we're going to explore, we're going to talk about the conventional hydroxide sulfide precipitation chemistries. Those are long-standing go-to products that we use, like sodium hydroxide, calcium hydroxide, or lime, and then the different sulfides like sodium hydrosulfide for precipitating metals. Some of the newer chemistries that are working their way into more prevalent use are DETC, or diethyl dithiocarbamate, dimethyl dithiocarbamate, or DMTC, and STTC, which is sodium trithiocarbonate. This particular product is unique in that it is not as toxic to microorganisms as the previous two, where they are very toxic. So the tightening of lead restrictions, as I said, I wanted to cover a lead acid battery manufacturer that had a conventional hydroxide precipitation process in a circular clarifier. They happen to comprise 80% of the local municipal wastewater treatment influent. And the State of Environmental Protection in Pennsylvania came to them and said, you must lower your limits to 0.015 milligrams per liter. So the conventional chemistry was no longer effective and resulted in a change in their process. They went to ultrafiltration and initially tried to treat the waste stream with just ultrafiltration alone, and they were not successful in getting down to these new limits. So we then looked at a metals precipitant in front of the ultrafiltration unit. We were able to successfully get them down to where they needed to be, but as a result of precipitating more lead, we saw that the ultrafilter was blinding faster than it had. And what I mean by blinding is you're passing water through a filter and you're adding solids to it, it'll eventually shut the pores of that filter down. And that process of pushing water through is called flux. And that is measured. They can monitor their flux rates. And as they see the flow go lower, they know they are starting to blind their filters. So it results in having to take the unit offline and clean it. So one way that we went about correcting that problem was we looked at the use of an aluminum chlorohydrate iron blend, and I tested that in the lab using the same porosity membrane filter, added the ACH at a desired treatment range, and measured how fast I could pass 100 milliliters of water through that filter. I also did it with just the metals precipitant present, and I did it with untreated water. And the result was that, in fact, the ACH gave us better and faster flux rate, and so we moved to that. And that was very helpful in keeping the plant running, because at the time they were actually having to haul their waste stream off the premises because they could not keep up with the influent. Next slide, please. So the next case limit that I'd like to talk to you about is the new nickel limits that I saw imposed on a high-end brass manufacturer. This customer was known for making very fancy lamps. They made wall plate covers, outlet covers, and they wound up having to change or move some of their product line from brass to nickel because customer tastes had changed, and that was more in demand. So they installed a nickel plating line, and plating lines have a lot of chemistries in them, one of which is chelants that will tie up metals and other unnecessary or unwanted things that could plate themselves out on the metal and cause a tarnish or a stain. So that presents a challenge for us as water treaters, in that everything gets chelated, including that nickel. And the conventional way of breaking a chelant bond would be to depress the pH to 4, maybe add lime as a precipitant, driving the pH back up to 10 to 10.5, and that also ties up the chelant, because chelants do like calcium. So the conventional chemistry, or doing it that way, was not going to get them into their new limit of 0.05. They had a lamella clarifier, settling clarifier, and they were not going to change from that. So it became important that we find something that would get them down. In this case, I looked at all three of the previous metals precipitants, the diethyl dithiocarbamate, the dimethyl dithiocarbamate, and the trithiocarbonate. And I found that the trithiocarbonate was very touchy, because if you overfeed that, you can actually do the exact opposite of what you're trying to do, and you'll disperse the metal. In the case of the dimethyl dithiocarbamate, it performed much better. The diethyl dithiocarbamate performed as well, but the DMTC really showed itself to be the one to use. However, I was creating a very fine flock, and so I used a little bit of aluminum chlorhydrate to create a larger flock so that our flocculant polymer could then grab these polymers and settle it out. And as a result, we met our new limits. So to summarize for you, tightening metal restrictions are bringing new challenges to us as water treaters. We can be the solution person for your customer. Metals such as molybdenum, nickel, and lead are coming under particular scrutiny. The elimination of molybdenum as a tracing agent or corrosion inhibitor is on the way, and it's causing us to look in other directions. The use of metals precipitants can aid you and your customer to meet the new discharge limits. And as water treaters, we need to have these tools in our box and be the problem solvers that our customers look to us for, and enhance our image in their eyes. Thank you for your time.
Thank you, Tom. I have to unmute myself. Thanks, Tom. Next up, we have Katie Keller, who's going to discuss treatment approaches considering soluble and insoluble contaminants. Katie?
Thanks, Brian. Good afternoon, everybody. So today we're going to start by discussing the difference between total, soluble, or insoluble contaminants. Total simply means the entire amount of contaminants, both soluble and insoluble. When talking about soluble, that refers to contaminants that will pass through a 0.45 micron filter. And then lastly, insoluble are contaminants that will not pass through that same filter. As a simple rule of thumb, just remember that soluble means dissolved. Dissolved contaminants are more difficult to remove, and so they're the object of many wastewater treatment methods, is to render these particles insoluble so that they can indeed be removed. There are a few reasons why it's useful to know whether or not you're dealing with soluble or insoluble contaminants or both, and then the approximate amounts of each. For example, how best to proceed with testing. That tells you where to start. Determine possible treatment chemicals. You'll be able to determine where to start in your test kit. Determine if the present treatment chemicals are adequate. Different bench scale treatment techniques require different equipment when scaled up to plant level, so you really need to know if your bench test is scalable. Determine if the present treatment plant or equipment is adequate. Only precipitation will remove soluble contaminants. And then this last point here is really a game changer when it comes to product selection. If you have a soluble or insoluble zinc, for example, and you're using an epipolyammine or an organic coagulant, you're not going to be able to touch that soluble portion of the zinc at all. Here we see an example with phosphate that's in the soluble state. So one can't really detect dissolved phosphate on site, even if you know or suspect that it's there. Since coagulation involves charge neutralization, we're bombarding the water sample with cationic ions to render the phosphate insoluble. This addition of cations can come from a variety of coagulants, both organic and inorganic. In this situation, an inorganic aluminum-based product was used with good results. So here you can see that coagulation has taken place, and after a flocculant is added, the phosphate settles into a mass at the bottom of the beaker. In this slide here, we're seeing the phases of treatment that was described in the previous pictures. So in photo number 1 here, we have raw wastewater, cloudy and obviously in need of clarification. After the coagulation or the charge neutralization begins to occur, we see a pin flock starting to form. This is the sign that what was previously soluble or dissolved is now making that transition into the insoluble state. It's in this form that the contaminant can be addressed more easily and either settled or floated for removal through the addition of a flocculant. So photo number 3 shows the agglomeration of the insoluble matter into a flock, which gravity then assists to the bottom of the beaker, which you're seeing in photo number 4. This slide is simply showing the visible difference between water with soluble contaminants and one where these constituents have already been rendered insoluble. And then just noting here that it's important to note that the coagulation phase of jar testing requires high shear mixing for maximum effectiveness. Flocculation, by contrast, requires a slow tumbling mix speed for best results. So here in this slide, we're looking at how you determine whether you're dealing with a soluble or insoluble contaminant. Fortunately, there is a definitive way to tell. Since we've previously determined that soluble refers to anything that can pass through a 0.45 micron filter, we're simply filtering the sample through filter paper and then testing for the contaminant of interest. So if you're interested about zinc, you're running a zinc test, phosphate, run a phosphate test, and so on and so forth. What does testing for contaminants without filtering tell us? It's telling us it's telling us the total amount of contaminants in the sample, so both soluble and insoluble contaminants. And then what does testing for contaminants with filtering tell us? This is telling us the total amount of soluble contaminants, and it's also helping us to estimate the precipitant treatment dosage that will be needed. And next, what does the difference in the unfiltered versus filtered test tell us? So that's going to tell us the amount of insoluble contaminants. Here at the bottom, there's just a really simple example. So if your contaminants without filtering is 100 ppm total, Your contaminants with filtering are 75 ppm soluble, and then the difference is that 25 ppm that's insoluble. So simply put, once the sample is filtered, you can better determine where to start in product selection for your testing protocol. Certain coagulants address soluble contaminants better than others. So it can be a time saver and lead to a much more effective treatment program. It's really a deliberate approach to a process that is all too often hit or miss, or like a bit like throwing darts. When looking at the treated sample, there are a few things to remember. If the filtered sample contaminant test results are too high, it means the precipitant program needs addressing. So remembering the point about organic versus inorganic coagulants, organic coagulants will do nothing for soluble particles. Organics have other uses, more like removing oils. And then to the second point, if the filtered sample contaminants are acceptable, the unfiltered results are too high, then that tells you that the coagulant or flocculant program needs addressing. To summarize our discussion, we've just included a really straightforward testing chart. It's simply showing the total contaminants include both soluble and insoluble, and filtering the sample will reveal the soluble components, and the difference between the two is the insoluble. So knowing what you've got is the first step in devising the most cost-effective treatment plan for you.
Well, thank you, Katie. Finally, we've got Kevin Cope, who's going to discuss water reuse and conservation. Kevin?
Thank you, Brian. Appreciate the introduction. Well, putting the number up there, 1978, this is not a new concept. I started in the water treatment industry in 1978, and one of my first projects that I got involved with was actually water reuse projects. So although we hear water reuse, water conservation, early on in my career, very early on in my career, I was involved with water use, with a water reuse project. And it was actually a very large petrochemical plant that I was the service rep for. They were having extremely high wastewater treatment costs. Their polymer cost alone for the use in their waste treatment plant was in excess of $1 million per year. And this is 1978. I guess I should have maybe have done a calculation to put it in real world numbers for today. But at the time, that was a massive amount of money for people to be spending on their polymer for a waste treatment plant. They did have very limited equalization, which really did cause some of the big swings in the application. But what we did is we were able to identify there were 7 wastewater generation sites within the facility. One was the boiler, the other one was the cooling, but the other 5 sites all came from production, different areas of production in the plant. Surprisingly, this was a very good situation for us. We had very good flow monitoring on all of the waste generating streams. Back in the old days, we had the V-notch weirs, and we went out and were able to get a basic idea of flow from every one of the generators, even the boiler and cooling blowdown. So going into this project, we had a pretty good understanding of the amount of water and where it was coming from. So what we did is we obtained samples from each one of the generated areas. We then made a test sample using the 7 generated where they were coming from. In other words, we took the 7 generated samples and mixed them together to form as close as possible to the actual wastewater that the waste treatment plant was seeing. And surprisingly, we were actually able to come within 10% of 10% plus or minus of the actual wastewater. So when we tested the actual wastewater and then tested this sample that we generated, we were about 10% either plus or minus on the actual water itself, which was excellent. So then what we did is we removed each generated sample and tested that to see if we could remove the material from the water. Now, in the case of the boiler and cooling water, we really didn't do anything there because there was really nothing to remove. Most of the materials there were soluble. We were looking at trying to remove some of the insoluble materials, kind of talking what Katie was just discussing. And so what we did then is one by one, once we treated the sample, we would put that treated water at the amount that was in going into the main sample, and then tested that wastewater to see which one of the generators or which generator or how many generators were causing the major problem for the polymer use at the waste treatment plant. So again, we tested all 7, putting them in one at a time, redoing it to get an understanding of what was causing us the biggest problem. We found that one of the 7 waste generator streams contributed to 60% of the wastewater polymer usage. What was nice about this is then what we did is we actually went into the plant and we were able to set up a satellite feed of a different polymer, interestingly, to that particular system, that particular generator. And luckily, they had an API separator. And if anybody doesn't know what an API separator stands for, American Petroleum Institute. And it's nothing more than a wide spot in the line that allows oils or solids to settle out to take loading off the system downstream. So here we were actually lucky that there was an API separator there. So we were actually able to pre-treat this material before and remove the contaminants before it got to the main waste treatment plant. Now, where does reuse come into play in this? Well, this cleaner water that we're able to produce, we then use for cleaning and washing the floors, the equipment in that general area, and eventually that water then did go to the waste treatment plant, but the majority of the contaminants were taken out of it. The major contaminants were coming from production, not from washing down the plant or washing down the floors. So by removing the major contaminant, we were, number one, able to reuse water. It didn't have to be city water. The water that we were generating was excellent for cleaning down the floors. But what was really impressive is we were able to reduce the wastewater treatment cost by 20%. Would have loved to have said we reduced it by 60, but in all reality, we were able to reduce the overall waste treatment by about 20%, which was at the time, and at this time, I wouldn't even think, was a very, very nice sum of money that we were able to accomplish. So that was a petrochemical plant. In my career, I've also done some water reuse in industries such as the industrial laundry industry. And what happens there, a lot of times the customer will take the final wash water, which is relatively clean, but then use that in the first wash station, saving money, saving water, reusing water. And another added benefit is also recovering heat from the wash waters. So you heat the water up, majority of the industrial laundries will use hot water. So in the reuse of water in industrial laundry, we find that they can only reuse the water, but also conserve some of the heat that is generated for the washing. This was another really interesting one on water reuse and water conservation. Worked in a dairy farm, at a dairy manufacturer, actually a cheese plant. And they were using their wastewater to make down their polymers. Well, for the most part, it was okay, but every time there was an upset, we would have a problem making down the polymer because the water was basically dirty. They would then have to go to city water, which was costly, and would cause a problem. We found, believe it or not, that the use of the cow water was a much better choice. It was water that was basically being put down the drain. We then used the cow water, used that for the polymer makedown, conserving water, and then reusing that water rather than sending it down the drain. At a steel mill, this is a very interesting application. The mill had a chrome reduction recovery system, and there was a decision made that that water was no longer going to be put to a waste treatment plant, but rather put into the cooling system. Well, what we did was then take a water modeling program to see how that would affect the water going into the cooling system. What adjustments did we have to make to our treatment program that we need to be aware of once this chrome wastewater started to coming into cooling water? And we were lucky there was a minor amount of adjustments, but the adjustments still were needed, and use of the water modeling program gave us some direction on really what we needed to do to change our treatment program and the cooling system in the steel mill was in a caster recycle system is where that was at. And I've also used numerous wastewaters used for cleaning within the facility. If the water is relatively clean, can we use it for cleaning? Can we add a little bit of something to it to help it clean different areas, cutting down on the use of city water and reusing the water from the plant? So an observation that I've had is when you start talking reuse to people that are not in our industry, and most people in our industry think that we call it a municipal plant. When you talk about reusing wastewater, the first thing people shout or go to is, "I'm not drinking that." Well, in the case of reuse water, I don't think we're trying to make drinking water. We're trying to find areas that water can be reused in different ways that saves and conserves on the amount of water that's needed inside a facility. So one of the things I always say when talking about water reuse is we must start thinking as wastewater now as a pretreatment plant. What do we do in the waste treatment plant to make a better water that potentially can be used in the facility? How can I make a better water, not just meet discharge limits? Too often, and my background is both boiler water, cooling water, and wastewater, but the mentality of wastewater is, let's meet the discharge limits. How do we meet those? What adjustments in our chemical program at the waste treatment program, how will those affect the water treatment chemistry? How can we make adjustments that improve the water quality so potentially it can be reused? We must consider the water chemistry, understand the chemistry of the water, and understand what limits that will put on us for reuse. Would switching from ferric to ferric chloride instead of ferric sulfate be a benefit? Is there a chance for calcium sulfate scale in a system that's using ferric sulfate? Could you switch to ferric chloride, still maintain the use of an iron salt, but changing the chemistry from sulfate to chlorides? Would an organic coagulant work better than an inorganic? Conversely, would an inorganic work better than an organic chemistry? Looking primarily at the water chemistry. Another thing, how will this change affect the water chemistry? What do I do to affect that water chemistry? And lastly, we hear this all the time. When you're doing water recycling, the process changes can even become more critical to understand what a process change could do to changing the water chemistry for potential water reuse. So my recommendations when we talk about water reuse or water conservation is really first key is to have a plan. Understand what you are trying to do. What are you trying to do with your program? Are you trying to conserve water? Are we trying to use water, reuse water? What are we trying to do? Another thing to do is identify potential areas of reuse. Where can I reuse water? What are areas that we can bring water to that aren't as critical? And what I mean by that is when I look at a plant, I'll tend to order from the least critical to the most critical. You're probably not going to take the wastewater right out of your waste treatment plant and stick it in your boiler. But understand, is there an area within the plant that clean wastewater could be used? So sit down, look at all your potential applications, where water is being used and where potentially can I reuse it. Also identify the amount of water that is required and or the amount of water that's generated. If you're required a lot of water in this area, but you're only generating a small amount, maybe just that small amount fed into the water being used could be considered water reuse. So take a look at the amount of water you're generating and how much water is required for various applications. So another key that I found very useful is map the location where the water is generated. If you're generating water on the west side of the plant, but there's a great opportunity on the east side, and that east side to west side, in the case of some of the steel mills back in the old days in Pittsburgh, is 9 miles, probably not a good idea to try to reuse the water 9 miles away. But again, same thing, map the location for potential use. Figure out where I can use, where are some of the non-critical areas to get this program working, to get started on making potentially for water reuse. Look for small reuse opportunities. Try to get the small reuse first, and then work into the big ones. Build confidence in yourself, build confidence in your program. Areas of ideas might be polymer makedown. Could we use some wastewater to make down a polymer? Are there foam control sprays in the plant? Could the wastewater, a clean wastewater, be used in the spray system for foam control? Again, a biggie is floor cleaning. Can I use a cleaner wastewater to do floor cleanings? Also the same thing, equipment cleaning. Is a potential the use of using a relatively clean wastewater to clean equipment throughout the facility. One of the things I always like to recommend is have a water chemistry run on the wastewaters. Do a full analysis. Do alkalinity, do hardness, do oil and grease, do pH, do a variety of different, but basically a full water chemistry that you would run for a wastewater, for a cooling water system. And look and compare those to what the current water requirements are. So if you have a cooling water system and you know what the water requirements are for that, compare that to your wastewater requirements and see how they match up, or if they match up, or are there changes that I might make in the waste treatment plant that might allow me to meet these water treatment parameters. I'm a big fan of using a water modeling program to find out if-then scenarios. If I change this, what potentially would happen, or where potentially could I use the water? And with that, I thank you for listening, and I will turn it over to Brian and see if there were any questions during our presentation.
Thanks, Kevin. We do have some questions. So let's see here, in no particular order. Okay, here's one about metal precipitants. So I guess this would be for Tom. Tom, the question is, how do I know which metal precipitant will work best for a specific metal?
It's a good question, and there's no real definitive answer to that, although some of these particular products do have a better affinity for certain metals than others. And really the best method of determining that is testing them all.
Oh, okay. All right, so here's a question for, let's see, when running a water analysis, what are the important items to include? So I guess maybe that could be for Kevin.
Yeah, I kind of mentioned a little bit. I would think alkalinity, total hardness, calcium hardness, magnesium hardness, pH, chlorides, sulfates, sodium. Those are ones I was trying to come up with when I was giving those off. But just look at it like you would be running a normal water analysis for a cooling water makeup. So those are just some. And then, you know, if you're in a plant that is a refinery, you might want to run oil. You know, one of the things we're seeing now in the waste treatment industry a lot is barium. So potentially run barium. Silica, take a look at silica. So just again, take a look at a general water treatment analysis that you would run primarily for a cooling tower makeup. Okay.
All right, thank you. Here's a question about filtered sample. Okay, how much filtered sample do you need for a test? And I think that that's speaking to the soluble versus insoluble. So Katie, can you field that one?
Sure, yep. So really the answer is it depends on the test you need to run. So if you're running the BOD, you need about 500 milliliters, where if you're running something like zinc or phosphate, you need about 10 milliliters. As a general rule of thumb, more is really always better, just in case you have a problem that pops up in the middle of testing.
Okay, thanks, Katie. Let's see, here is a question about BOD, I believe BOD. So what dollar amount are some food companies seeing in surcharges? So I guess the magnitude of the fines there.
Yeah, so that's one thing you want to talk to your customer about. If they're paying $100,000 and they're discharging 2 million gallons a year, you might want to let them know that's not a bad deal. If you have a customer that's doing, 1,000 gallons a day and they're paying $250,000 a year in surcharges, that's definitely something you want to talk to. We're seeing a lot of food customers out there that are in that $250,000 to $500,000 range a year. And that's a really good customer to help them find a solution that will kind of solidify you as their guiding partner for the future.
Okay, I guess a related question would be, if the food customer lowers their BOD discharge rate, is there a chance the municipality is just going to increase their fees?
Absolutely. Before they start this process, you're really going to want to either encourage your customer to sit down with the municipality or go in there with them to have that discussion. You want to make sure that if the plant's at capacity, then they will more than welcome you reducing your discharge or BOD to their facility. If they're just doing this as an income and it's in the budget and they've counted on it, that is going to be a really rough conversation with them. And you're going to want to start building up that relationship with the municipality right away.
Okay, thank you. Let's see here. So somebody wants to know, how do metal precipitants work? So Tom?
Another good question. What they are is very strong reducing agents. And what they are doing is reducing the valence state of the metal and making it insoluble by doing so. And I wanted to add on a little bit about the question whether and which one to use or how to determine which one to use. As I said in my presentation, the lead acid battery manufacturer, both the diethyl dithio and dimethyl dithiocarbamates worked. But what really wound up bringing it home was that the DMTC is 40% active and the DETC is 25% active. So we used a lot less chemistry.
Okay, thank you. And somebody, in reference to Kevin's segment there, somebody wanted to know what was causing the high polymer demand at the tough wastewater generator.
Okay, I do actually remember this because it's things that kind of ingrained in your mind, for your career. It was actually a sulfonate sump is where we found to have the biggest problem. It looked like what was happening was it was acting very much like a surfactant and really just chelating and tying all the oils up throughout the waste treatment plant. Once we removed, and we had a relatively high dosage at the sulfonate sump of polymer. Once we got the majority of that out, it really allowed for relatively easy to break the bonds once the water got to the waste treatment plant. So it was a sulfonate sump is where it was at.
Okay, thanks, Kevin. Somebody wanted to know if we could also cover the relationship of BOD and COD. So I guess that would go back to Dick.
Right. So generally it's different for every wastewater stream. Although I think in the municipal wastewater, generally COD can be counted on as being around 1.5 times as strong as BOD. The more industrial that you get, the more that can change. So if you have a fairly consistent stream, you could test BOD and COD at the same time over a period of weeks and determine what your ratio is. And then you could go to only testing COD in-house if you wanted internal numbers, and it would be fairly reliable. The benefit of that being a COD test is about 3 to 4 hours, whereas a BOD is generally a 5-day test, quite often that you would have to send out to a lab if you didn't do in-house and have your own refrigerator for.
Okay, thanks, Dick. Let's see. Well, it looks like we're just about out of time. Here's one. Somebody was asking, Tom, why did you use ACH instead of alum in that plating operation example?
Yeah, Dick had typed in a good answer in that it will create less sludge, but really the function or vehicle that results in that is that if you look at these two chemistries on an Al2O3 percentage basis, alum is generally going to be around 8% as Al2O3, and ACH will range from anywhere to 20 to 23% as 0.03. And as a result, you could basically feed 1/4 the feed of ACH that you would feed of alum to get the same result, and thereby generate less sludge.
All right, thanks for clarifying, Tom. Pun intended. So here's a question regarding PO4 levels. So what levels for PO4 can be removed via coagulation, percentage-wise? So Kevin, can you feel that?
Sure. Really, the answer would be it's all over the place. Done a lot of work with phosphate removal in my career. I'm a big fan of the use of the aluminum-based materials. I've done it with aluminum-based, I've done it with iron-based, and I've done it with lime. But I find the aluminum-based, the PACs, to be the best, although I've had some success with the sodium aluminate also. So to say what percentage is really difficult, I mean, you really need to go out and run the tests, look at those, well, I want to say 3 chemistries, but really 2. I mean, I think lime really doesn't do a great job, but use of the ferric chloride, ferric sulfate, but really look very hard at the different options you have as far as aluminum-based, aluminum sulfate, alum, PAC, polyaluminum chloride, aluminum chlorohydrate or ACH, and or sodium aluminate. So it really will vary on how much you can take out based on the system, but then also based on the chemistry that you choose to use. So I hope that helps and answers the question. But I've seen it remove quite a bit and get it down, significantly get it down.
Thanks, Kevin. Well, it looks like we're just about out of time here. If any questions didn't get answered during this production time, we'll reach out to you via email. If anybody, Kevin, do you have contact information for requesting a copy?
Yes, it would be, let's see, yeah, if we go one more slide. My email address is there on the bottom right, the kcope@brentag.com. Please send me an email. We will more than likely have the video of this up on YouTube at some point over the next several days, but there is a PDF form or version readily available. And again, we'll more likely be putting this up on YouTube within the next few days. So please feel free to email me and I'll get that off to you.
Great. And I want to thank everybody on behalf of Brentag North America for devoting some time for this experience today. It was our pleasure, and we'll be doing more of these in the future. The one for the next quarter will be announced probably in the next month or so. And if anybody has any ideas on programming, we'd love to hear from you. All right, with that concludes our webinar. Everybody have a great rest of your day.
Thank you.